Hi, welcome to Unit 7, Day 4. This is Part 1, Mass-to-Mass Reaction Stoichiometry Introduction. So as you know, we've been studying stoichiometry in this unit, and stoichiometry involves using mole ratios to convert from the amount of one thing to the amount of something different. And when we first started this unit, we used the subscripts in a chemical formula for the mole ratios to solve problems like you see here. Now what we've started doing more recently is using coefficients in the balanced chemical equation as our mole ratios to solve problems like you see here. So today what we're going to do is we are going to tackle what are called mass-to-mass problems. In the previous lesson, what we did was we tackled what were called mole-to-mole problems. So we were given the mole of something and we're trying to find the mole of something else using the coefficients in a balanced chemical equation. Now we're going to be given the mass of something in a chemical reaction and finding the mass of something else in that chemical reaction. And so that's why they're called mass to mass. Okay, so before we begin, remember stoichiometry involves two types of knowledge, both conceptual and problem solving. We are going to focus on, in this video, the conceptual aspect. Later on, you'll watch videos where you look at example problems and do some practice, and that's where you're really going to tackle the problem solving. But we're focusing more on the conceptual understanding first here. So in terms of the conceptual understanding, it's helpful for us to use the analogy between chemistry and cooking. So whereas a chef uses a recipe, a chemist uses a balanced chemical equation. Whereas a chef would use ingredients, chemists use reactants. And whereas a chef makes food or dishes, a chemist makes products. Now, having that understanding in the back of our mind is helpful in learning how to read the problem, interpret what the problem is asking us, and figuring out the key information provided by the balanced chemical equation. So what we're going to do to sort of tackle that is we're going to look at some CFUs where we alternate between a cooking scenario and a chemistry scenario. So you can see the analogy between the two for both types of problems. So here we have in our first CFU, at the top we have a recipe for making grilled cheese sandwich. So you have 2 slices of bread and 1 slice of cheese. These are your reactants. They're on the left side of the arrow. And then our product of the food that we're making is the 1 grilled cheese sandwich. So this is a recipe and it's sort of written like we would write a chemical equation. Now, of course, there are other things that you may want to put in a grilled cheese, like using butter or whatever. But this is sort of give you a basic idea of our ingredients and then the food that we can make from it. So the question is, if one were to follow the recipe shown above, describe how much of each ingredient you need and how much food you can make. So basically, according to the recipe, how many slices of bread do you need, how many slices of cheese do you need, and how many grilled cheese sandwiches can you make? Go ahead and pause the video now. When you press play again, the answer will be revealed. Great, so you can see from the recipe you would need 2 slices of bread, 1 slice of cheese, and you can make 1 grilled cheese sandwich. And you're using the numbers that sort of in front of the ingredients and the food that you make. Similarly, we can answer a question that involves a chemical reaction. So here we have a balanced chemical equation, which again is like our recipe at the very top, and it's showing us the balanced chemical equation or the recipe for making ammonia, NH3. So if you were to follow a balanced chemical equation shown above, describe how many moles of each substance you would need or could make. So how many moles of N2 do you need according to this equation? How many moles of H2 do you need? How many moles of NH3 can you make? Go ahead and pause the video now. When you press play again, the answer will be revealed. Great, so you can tell just from the coefficients, there's an invisible 1 in front of N2, so that means you need 1 mole of N2. There's a 3 in front of H2, so that means you need 3 moles of H2. And there's a 2 in front of NH3, that means you can make 2 moles of NH3. Because remember, these coefficients are our molar coefficients. You can think of them in terms of the moles of things that you use or moles of substance of product that you can make. Now, recipes like balanced chemical equation give you a guideline for making a particular dish or product. However, when you're cooking, you don't necessarily have to follow the recipe. You can scale up the recipe, which is to increase it, or scale it down to decrease it based on how much of the ingredients you have and or how much food you want to make. For example, let's say in your kitchen you have 14 slices of bread. So using this recipe, how many slices of cheese do you need to make grilled cheese sandwiches with the 14 slices of bread? Go ahead and pause the video now, and when you press play again, the answer will be revealed. The answer is 7. So what you did in this case is, according to recipe, you need 2 slices of bread, but you have 14. So you would have scaled the recipe up by a factor of 7, because 2 times 7 gives you the 14. So then, since you've scaled up the bread by 7, you also have to scale up the cheese by 7, so that will be 7 slices. Now, you can also solve this using dimensional analysis, and my work for that is shown here. And the reason why I'm showing that to you here is because I want you to see that dimensional analysis can be used for simple problems like this that you can do mentally, or for more complicated problems. But seeing it for the simple problems may make it a lot easier to understand when you're doing it for the complicated problems. So if you want, you can just pause the video and take a look at the work shown for dimensional analysis. All right, let's try this now for CFU 4. So in this case, you're now in your lab, no longer in your kitchen because it's a chemical reaction, and you have 15 moles of H2. So how many moles of N2 would you need? This is similar to the problem when you were dealing with the grilled cheese, when you had 14 slices of bread and you were trying to figure out how many slices of cheese you need. Now we have 15 moles of H2. How many moles of N2 do you need? Pause the video now. When you press play again, the answer will be revealed. The answer is 5. So in this example, what you did was you scaled up the reaction by 5. And the reason why we know that is because the recipe calls for, or the chemical equation calls for 3 moles of H2, but you have 15 moles of H2. So to go from 3 to 15, you had to multiply the moles of H2 by 5. That means you have to multiply the moles of N2, that 1 mole of N2, by 5 as well. And again, you can solve this using dimensional analysis, and the work for that is shown at the bottom, so you can see what it looks like doing this with dimensional analysis. And if you want, you can pause the video and look at that work. So in the problem that we just saw, CFU 5, we did what was called that's called a mole-to-mole reaction stoichiometry problem. We started off with 15 moles of H2, and we're trying to find the moles of N2. So we're converting from moles of one substance to the moles of another substance. But in the lab, chemists don't actually measure out moles of their reactants and products. They usually weigh their reactants and products to get the mass. So therefore, in reality, when we're doing these problems, we actually have to do more problems where we're converting from the mass of something to the mass of something else. And these are called mass-to-mass stoichiometry problems, and that's what we're going to tackle today. So in terms of the process of solving these types of problems, it's pretty much the same process you've been looking at for all stoichiometry. You're going to start by converting the amount of your given to moles of your given using the mole map. And specifically, since these are mass-to-mass problems, we would use the molar mass. So we would use this part of the mole map. Going from mass to moles, we would go through the molar mass. Now, the next step is to go from our moles of given. Since we found the moles of given, we now need to go from moles of given to the moles of fine. And this is where we use the mole ratio. And in our case, these will be the coefficients in the balanced chemical equation. Now, since we need to use the coefficient to balance the chemical equation, the chemical equation must be balanced. So we always have to check that. Finally, we want to convert from our moles of fine to the amount of fine, again using the mole map, and we would use the molar mass for this problem because the amount of fine will probably be asked for it in grams. So let's look at an example scenario so we can see where this would play out in a lab. Let's say a student is performing the precipitate reaction above, and the student weighs out 5 grams of potassium iodide, 5 grams of Ki, and they want to know how many grams of PbNO3 does this do they need to weigh out for this reaction? So here is the student. They have their potassium iodide. They take out some and they weigh out 5 grams. So they have 5 grams of potassium iodide. So now they're asking themselves, well, okay, the next thing I need to weigh out is lead nitrate. Well, how much of this do I need for the 5 grams of Ki? So to solve that problem, what they would do is they would follow this process: amount of given to moles of given to moles of fine to the amount of fine. So the first thing is to convert from the mass of Ki to the moles of Ki using the molar mass, which we get from the periodic table, 166.0 grams of Ki. And the work for that, if setting it up as a dimensional analysis problem, would look for like this, going from mass of Ki to moles of Ki. Now that second fraction here comes from the conversion factor, and then they would multiply those two fractions out to get 0.0301 moles of Ki. Next step is to convert from moles of Ki to the moles of the lead nitrate. So now they're trying to find the moles of their fine lead nitrate, PbNO3. And here they would use the mole ratio in the balanced chemical equation. So they go and look at the coefficients. They see there's a 2 in front of Ki, so that's 2 moles of Ki, and there's a 1 in front of PbNO3, so that's 1 mole of PbNO3. And the work for that is shown here. So they would take their moles of Ki that they found in the previous problem and multiply it by the conversion factor that they got from the coefficients in the balanced chemical equation. And that would give them the moles of PbNO3, their moles of fine. So now they're here. They've got their moles of fine, so now they need to find the amount of the fine using the molar mass of the PbNO3. And so the molar mass, if you go to the periodic table, you'll calculate it to be 331.22 grams. And so their work for that is shown here. They would take the moles of PbNO3 that they got from the previous step, multiply by that conversion factor to get the mass of PbNO3. And so they get 4.99 grams of PbNO3. Now they can do this sort of step-by-step fashion that you just see here, or you can also, of course, solve this in one step, and that's sort of shown above what that looks like. If you want, it may be a good idea to pause the video and compare the one-step method above with the step-by-step method so you can see how the two sort of line up. All right, let's look at one last example of problem. So the student is performing that precipitate reaction. They weighed out the 5 grams of Ki, and they also determined, as you saw in the previous step, they need 4.99 grams of PbNO3, and they weighed that out. So they've got their PbNO3, they weighed out 4.99 grams. Now what the student wants to know is, the student then dissolves the 2 compounds in water to make a solution, and then mix it together to form the lead iodide, which is that yellow solid precipitate. So that yellow stuff in there. And now what they're asking is how much lead iodide precipitate could they theoretically make from 4.99 grams of lead nitrate? So to answer that question, again, this is a mass-to-mass problem, so they're going to go from the mass of lead nitrate to the mass of lead iodide. Okay, so the process is the same as before. We're going to start by converting our lead nitrate to our moles of lead nitrate using the molar mass. Then we're going to convert from the moles of lead nitrate to the moles of lead iodide. In this case, we're going to use the coefficients in the balanced chemical equation as our mole ratio. So we see that there's a 1 in front of lead nitrate and a 1 in front of lead iodide. They have a 1-to-1 mole ratio. And so for our work for that will look like this. We would take the moles of lead nitrate we got in step 1, and then we would multiply it by that conversion factor there. Okay, now we have the moles of lead iodide. Once we have the moles of lead iodide, we convert from moles of lead iodide to mass of lead iodide using the molar mass of lead iodide. And so our work for that is shown here. We would take the moles of lead iodide and multiply it by the conversion factor we get from the molar mass. And then we get 6.96 grams of lead iodide as our answer. So that means from the 4.99 grams of lead nitrate, you can make 6.96 grams of lead iodide. So what you're going to do next is you're actually going to see more example problems like this done by hand, and you're going to watch that video and follow along. Then you're going to do the practice problems, and then finally take the exit ticket for these mass-to-mass mole problems. All right, that's it for this video. I hope you found it helpful. Have a quality day.